Hey everyone, welcome to the Dapr 1.14 release celebration. This is a virtual launch party where we've invited several contributors to demo the latest Dapr features they worked on. And we have two Dapr end users talking about their experience and the new Dapr release. With me is Mark Vossel, Dapr co-creator and maintainer. Welcome, Mark. You must be very excited about this new release.
Yeah, I'm super excited. We got a packed agenda today, actually. There are so many things in this release. It's one of the biggest releases we've ever done inside Dapr. And so we thought, wow, why don't we put this all together and celebrate these things? The thing about this is there's so much we could do. We couldn't fit it all into an hour. So hopefully you'll stay with us today. Just look at a little bit of an overview of what we're going to cover today. First off, we're going to dive into the Jobs API. This is a new API that we introduced into Dapr that allows you to schedule jobs. And this is backed up by a new service that we built inside there as part of the Dapr control plane, the scheduler service. We'll look about what that is and how to use it all. And we'll have Ollie from Dotmatics will sort of dive into a bit of the background of how he's been testing it. We'll move into actor multi-tenancy, how we'll make actors now multi-tenant across your environments. Dive into a great feature where we're looking at how you can improve your metrics and the filtering around that. Dapr Shared is not quite, it's part of the 1.14 release, but it's released in 1.14 timeframe. It's an alternative deployment models for Dapr. Move on to my favorite feature of this release, streaming subscriptions. It's a new way of consuming subscriptions that allows you to consume subscriptions in a code dynamic way. Love that. We'll touch on improvements to the Outbox pattern about how we can now send alternative shapes of messages at. And then we'll finish up with how to get hold of the release, what's happening with it all, and kind of the latest updates with it all. So packed agenda, Mark. Let's dive into the first session, shall we? And that's the new Jobs API with Cassie. So Cassie, take it away. Welcome.
Alrighty. Yeah, let's talk about the Jobs API and the scheduler service. My name is Cassie Coyle. I'm a software engineer at Diagrid, a part of the Dapr open source team. Let's talk about why we wanted the Jobs API and the scheduler service. We know we had a cron binding. It was pretty popular, but we wanted to expand upon that and make a first-class Jobs API to make that a better experience, more extensible. This could be used for several different types of scenarios, including but not limited to the list there with database backups, email notifications, maintenance tasks, batch processing. Whether you have a job you want to come back to you like one time or recurring, this is a great use case for it. And then another motivation and a really big one for us was to improve the scale of actor reminders. On the right, you'll see like a little snippet of the actors and workflows, like descriptions. So actor reminders are used to tell an actor when to wake back up. And it didn't scale as well as we had hoped horizontally. So this was a big motivator for us to improve upon. And then under the hood, Workflows uses actor reminders as well. And so if that doesn't scale, Workflows doesn't scale as well. So big push to scale these things. Now let's talk about the scheduler control plane service. It is a brand new binary. This new control plane service is deployed by default with the Dapr CLI, and I'll show this in the demo here shortly. It runs in both Kubernetes and standalone mode, and it runs as either a single instance or an HA mode, so like 1 or 3 instances. The capabilities for the scheduler is that it stores jobs to be triggered back to an app at some point in the future. And the scheduler guarantees that a job is triggered by only one scheduler. And this is done and accomplished by the implementation details, being that it has an embedded etcd database inside the scheduler process. So we have this etcd instance here. Note that you do not have to do additional configuration for the etcd. It will just auto-magically work. And then the scheduler uses this cron scheduling library such that as you scale the schedulers, it maintains who owns what jobs. So like the schedulers own a subset of all the jobs such that we guarantee this point here that a job is only triggered by one scheduler. So how do we use the scheduler? Well, you use it with the Jobs API. It is a brand new alpha API. You can schedule a job, get a job, or delete a job via both gRPC and HTTP. So here's that line there. Here's an example of how you would schedule a job. So we have a post here via our v1 alpha 1 jobs endpoint where I'm scheduling a job named test here, where I'm sending in some data, which is just a Google type expression with my name. And then I want that job to be sent back to me in 3 seconds. So from the app, it goes to the sidecar, and I know in 3 seconds, it'll come back to me via the on job event endpoint for gRPC or the /job endpoint for HTTP. So that's a bit about the Jobs API. If we put it all together, this is what we get. You can schedule jobs to be executed at some point in the future with the Jobs API and the scheduler service. Let's do an example real quick. Say we're doing a prod database backup, and that's the job we're going to schedule. From the app, we'll schedule that prod database backup either via gRPC or HTTP. It comes to Dapr. Dapr routes that job to the scheduler, says, hey, schedule this job, prod database backup. You know, maybe we want a monthly recurrence. That'll live in etcd, a month will go by, and then it'll come back via this streaming endpoint here, watch jobs to the sidecar. It's important to note that every sidecar connects to every scheduler because we don't know which scheduler owns which job. So we have to be watching for all of them. So that prod database backup at the month mark comes back to the sidecar, and then via a unary call, it goes back to your app via that on job event endpoint or the /job endpoint for either gRPC or HTTP. And then you do your own business logic based on the job you get back once, you know, it's at an expected trigger time. So that's the whole flow. Now let's do a quick demo. So I wanted to show the Dapr init with our latest RC version, showing that scheduler getting, you know, spun up. This is just my newly built Dapr CLI. We see that Dapr scheduler container is running perfect. So if I do a Docker PS, we see that my scheduler is in fact up and running as of 11 seconds ago. If we check out the logs for our scheduler, we see starting Dapr scheduler service with our latest RC version, you know, a little bit more info. So like log level, MTLS, our health metrics or health and metrics server are both running. It's starting up, listening on port 50,006 here. We're starting etcd. So now we're going to start to see some embedded etcd logs coming up here. That's all fine and dandy. We'll start to see some Raft logs because it's using Raft under the hood. That's all great. We scroll to the bottom, we'll see etcd server is ready, and we've started our etcd cron like scheduler library. Perfect. This looks good to go. Now let's take a look at our latest quick start jobs example. And we're going to, for this example, run a job service. So you'll see job service running. And what that's going to do is handle the consumption of the triggered jobs. So here's that main. This is Go code. We have our app port. We'll see 6200 there. We have a job handler. So that's /job. And then our handle job func. Then we're just going to listen and serve. So if we look at the handle job func, this is what's going to be executed once we get our job back. So we'll just output, you know, we received our job request. We'll read the body, then we'll unmarshal, then we'll decode our job data. And then we're simply going to print out our job, starting our droid, and then it'll be like the name, executing the maintenance job, which is our droid task. So pretty simple, but this is what's going to execute when we get that job back at trigger time. So let's go ahead and run this job service. So again, we have our Dapr run with the job service app ID and then our ports here, and then we'll run the Go code. Beautiful. We see that server started on port 6200. We're using our latest RC version, and then we see scheduler stream is connected. Perfect. So we know we'll get those jobs. Now, what I'm going to show y'all is just simply how to schedule, get, and delete some jobs. So let's schedule a job named R2D2. So we're going to hit that v1 alpha 1 endpoint and then schedule this job with a value in our data of an oil change. So this will be the task for our droid, and it's due in 2 seconds. So already 2 seconds has passed, and we've received our job request, starting our droid, that R2D2 job, with the maintenance job of an oil change. Now let's schedule a C3PO job. This one is due in 30 seconds, so I just spun it off. So yeah, C3PO with a data value of limb calibration due in 30 seconds. So that now should be in our etcd. We're just waiting for the 30 seconds to be ticked to get our job back. So in the meantime, while we're waiting, we'll just get that job. We'll ensure that it's in our etcd instance. Here's a get. We want the job that we just scheduled, so that C3PO job. And we did get that exact output from the one we just scheduled. Okay, perfect. So you do see that we did get it. 30 seconds since I scheduled it has passed, and you see that output now. Our job has been sent to our app. Perfect. Now, I want to delete the job. I don't want it lingering around. So let's run a curl to delete it, that C3PO job. Now what happens if I do a get? I want to get the job that I just deleted. Well, as expected, it's going to fail to get the job due to job not found. That's because I deleted it, right? So this is working as intended. And you'll see that same error here, error getting job C3PO due to job is not found. So perfect. We know that this works fine and dandy. Now let's kill everything and do an uninstall. Perfect. So we see we remove the container with our new Dapr scheduler and remove the volume if it exists. Alrighty, that concludes our quick demo. I did want to touch on, you can enable active reminders to use the scheduler service by enabling the preview feature. Here's an example of how that configuration would look like. You set scheduler reminders to be true, and then this enables the active reminders and workflows to scale. It's important to note that you can't use like the new system with the old, it's one or the other. So just important note there. Some key takeaways: we saw the Jobs API is used for scheduling future tasks and jobs, whether it's one time or like at an interval. And then we saw the scheduler service, which improves the scale for active reminders and workflows. And here's some links. I guess I'll open the floor for some Q&A.
Yeah, that was fabulous, Cassie. It's fantastic. There's a couple of questions here, at least one from Arnold. He says, is the etcd state store persistent, or does it rely on at least X instances to be up at all times? So what's the state persistence of the state store, and where does that state get stored?
It is persistent. So if you do have like downtime, that it'll come back up and have your data. You saw with the demo, like we're spinning up a volume and we are storing the data to persist across like restarts.
I'd love to ask you, like, this is fantastic that we kind of got a first-class API for jobs now inside there. And so, one thing is, this is going to go into the SDKs over time as well. Is it in which SDKs is it in so far? Is it in the Go SDK, or which ones?
Yes, so far it's in the Go SDK. We do want to get it across all of them, but that will come in the future.
And a lot of this was also about scale and design, wasn't it? And, you know, the fact that we wanted to kind of scale thousands of these things. Can you talk for a few moments about that before we dive into anything?
Yeah, so in the proposal, I've listed very hard numbers that we have done with our scale testing for like testing with scheduler and with workflows using scheduler. So those hard numbers can be found there in the proposal, in the Dapr proposal repo. Basically, we know that with scheduler, we can scale to like potentially millions of jobs. And, this means that we can schedule and scale to that number as well for like the active reminders and workflows using that under the hood. So really good performance numbers that we're seeing, and hopefully Ollie can add like his experience to using it.
Yeah, in fact, we'll sort of dive into that a little bit. Talking about some of the scale things around it all. One of the questions was, it's not possible to run the old and new reminders at the same time. But what if I do move to the new one? Does it mitigate some of the issues that we had with some of the scale? I guess we're going to find that out in the discussion with Ollie.
Yes. Yeah, so you have to use one or the other. You can't choose to use both systems for the reminder storage. I did want to touch on, we are at most limited by the etcd storage space, not like with the throughput of our reminders. So like the numbers I posted in the proposal is like as we scale horizontally, which is like the key thing this was built for, we do see performance improvements, whereas like the old reminder system would actually kind of like topple over, and the performance never improved after toppling over.
Okay, that's good. Well, for me, it's exciting because once we've now got a first-class API, we can sort of combine this as we do with other APIs. If you look at that, and so we'll be able to do things like scheduled messages for the future, and pubs of messages and other things like that. So I think it's great when you have a first-class API like this, because you can start to combine it with other APIs, like we've done, for example, with pub, sub, and state to create the Outbox pattern. Thanks, Cassie. So with that, I'll hand it back to you, Mark.
All right, so next up is Ollie, and he's going to talk about scalability and stabilization improvements for Dapr Workflow that is based on all this work. So welcome, Ollie.
Awesome. Hi, I'm Ollie. I'm just going to go into a little bit more detail about the work, the testing that we've done with the new scheduler, specifically in the context of workflows. A lot of you have been wanting workflows for a long time now, but we've been a little bit held back. So, why I'm here, I've been using Dapr since 1.8. I love contributing to the Dapr open source project. I don't do much dev these days, but I can test and break things really well. So under the hood, Dapr Workflows shares the same DNA as Microsoft's Durable Task Framework, which has been around since 2014. So there's already a great pedigree behind the Dapr Workflows runtime. Between 2019 and 2021, I was using Azure Durable Functions in my previous life at a previous company in a telco use case, pushing thousands and tens of thousands of workflows a minute. So in doing so, I flushed out many scaling and concurrency issues with the original Azure Durable Functions framework. So all of that to say, I've an idea. I'm no expert, but I have an idea of what matters when looking at the performance and the throughput of workflow systems. So v1.0, 1.10, sorry, 18 months ago, Dapr Workflows came out, and it really had limited concurrency. It was on fire. You could perhaps run one job at a time if you were lucky, without it all breaking down, which is to be expected of alpha software. But fast forward through 10.11 and 10.12 and up to the last release, 10.13, which came 4 months ago, the Dapr runtime has been optimized. It can do a lot more. Memory leaks have been flushed out, all through the great work of the open source community and some of the Microsoft contributors too. But unfortunately, that throughput increase in the runtime propagates down through all the subsystems that Dapr Workflows depends upon, and that includes the reminder subsystem, which, as Cassie's already explained, had to be changed, re-architected to support the new needs that Dapr Workflows was putting on at the actor reminder subsystem. So coming up to now, I've done some testing. I think everyone's going to be amazed by the throughput. I'm certainly very proud of what it can do compared to where it's come from. And there's still a little bit more time for some more tweaking as we approach GA. So looking specifically in 1.13, it reached ceilings, workflows are failing, and you couldn't scale the workflow app beyond one instance, which in our modern day, that's not acceptable. In 1.14, the throughput is better, much better. No catastrophic failures identified in the current release candidate. And you can scale the workflow app horizontally. You can add more instances and there will be no failures. So how have I tested this? The two main patterns that Workflows offers is the monitor pattern, or if you're familiar with the code, it uses a continuous new API. So it goes through a workflow, waits for a couple of seconds, and then loops again. That's one of the patterns that I've been testing at scale. So on one app instance, using the new 1.14 version, I could run 1,000 workflows concurrently in 5 minutes. Now, horizontally scaling that, what do we want to see? We want to see that number come down as we add more resources to get through that workload. And I can confirm the same workload, but across 5 instances, brings that down to 1 minute 23. And these are blended numbers over many runs. So there is a huge linear performance gain by horizontally scaling your workflow application. Second pattern, fan out, fan in. Super important. Take some work, distribute it over n number of nodes, and then wait for a result to come back in. In my test case, 10 activities all running in parallel, waiting for 3 seconds before the results gathered. So one instance on 1.14, 200 workflows running concurrently takes 1 minute. Once again, adding 5 workflows into that, 17 seconds. So we're better than a really good improvement there. So this is just to give you a taste of the improvements that have been made. Workflows are highly contextual. There's no one silver metric that, you know, we can say this is how fast it is. It really depends on your workflow and your workload too. But these statistics are going to give you confidence that we're heading in the right direction. So there's no reason now, from a runtime perspective, that workflows can't GA in 1.15, which will be the next release. So I encourage you to all take a look, give it a go, and please feedback through the channel's Discord and GitHub if you do find any issues using the language SDKs of workflows, and we really want to get that sorted in the next couple of months to make a really good GA. Thanks so much.
Yeah, thanks a lot, Ollie. This is really great to see these actual numbers in it that you've done with all your testing. So yeah, thanks you for putting in all this effort. It's really amazing.
You're welcome.
Love to see it. We're going to talk about active multi-tenancy now, and with you, Elena.
Thank you very much. Thank you for introducing me. My name is again Elena Kolewska. I am also a software engineer at Diagrid and a Dapr contributor. So I know that many of you have been already waiting for actors to become namespace aware, and I'm happy to share that Dapr can now do that. As of 1.14, we're all getting namespaced actors. So first, I would like to give a little intro on what actors are, because they're, you know, a relatively abstract concept that sometimes can be a little bit tricky to understand. A quick theoretical definition would be, and I promise this is just a really quick one, they're a primitive in the domain of concurrent computation, and they have a few important properties that are processing, so they can do processing, they can have state, and they can communicate. But what does that all mean actually for us? So I like to look at actors as an instantiated class, so something like an object. So this means they have their identity, they have state, they have behavior, right, in the classes. They can communicate to other objects, call other processes. The difference is in scope. So actors are not tied to a single process, but to the whole system. A single actor, which would be the actor ID, can be a single actor type, actually can be served by multiple Dapr instances, but an instantiated actor, which is the actor ID, can only be served by one of those many instances. So we would never get into a situation where multiple actor services try to manipulate a single actor ID, which could lead to a race condition. And all of this is built in the actor subsystem. It comes out of the box with Dapr. I know it does sound simple when you put it like that, but believe me, it's not. It only appears like that because Dapr makes it simple. In reality, it can be a little bit of somehow a tricky problem to solve. So in addition to that, actor execution happens in isolation, meaning there cannot be concurrent access to a single actor ID. Work is always going to be sequential, and that's very important to some use cases. Another important point, actors can persist their state across calls and across even the actors being rebalanced to different pods. So a few of the important properties are isolation, distribution of the actor IDs across the different pods, the scalability, state. And Dapr, so that's the general concept of actors, right? And Dapr here makes it even better. It's language agnostic, so we have, you can use the actors API with C#, Java, JavaScript, Python, Go, all of the bigger languages out there. You can also schedule periodic work with reminders and timers. So what are actors used for? Let's go through maybe a few use cases which can make it a little bit more obvious. IoT devices are a very common use case out there, and we are gonna see one with Joao in a little while. Session state is also a very good candidate to be represented by actors. Bank accounts by nature are very good candidate as well. We could have processing pipelines. We could even have space gloves. A very interesting use case for Dapr actors is, they're being used in the International Space Station. Astronauts out there in space are using Dapr to help with visual inspection of their gloves, which is kind of an important thing when you're going out in pure cold space on a spacewalk. Good, so now let's move to a little example of how the architecture look. Very simple use case here. So we would have, let's work with the IoT use case here. We're gonna have a smart bulb on the right, a smart light bulb that can be controlled with a mobile phone app. The mobile phone app connects to its backend on the left, and then there is an actor service that can control that light. So all of this is really simple. The applications have their Dapr sidecars, and there's this little thing called the placement service here, which is just a control plane service that, let's say, keeps track of which actors live where and where can they be found. And there's this little thing called the placement table here. Okay, and that's simple, right? Looks simple enough. You wouldn't really need actors for that. But what happens if you have millions of those lights? What happens if you have millions of users using your system, right? Then all of this becomes a little bit more complicated. And then you would have to scale out. You would have to scale horizontally. So all of those millions of users can try to switch their lights on and off and dim them and program them to turn on at a particular time, change their color even. So in order to handle all of that load, we're going to have to run multiple application instances, right? And thus multiple Dapr instances to support this load. So we have to scale horizontally. And when we do that, Dapr guarantees that a single light can only be controlled through a single Dapr instance. So we wouldn't get into any kind of race condition where different Dapr instances are gonna try to control the same light, or people pranking each other, which, by the way, is not a made-up story. It's an actual thing that happened to me with a smart bulb. Actually, it was a smart plug. Where my husband tried to prank me while I was turning it on and off again, but because there was isolation and sequentiality, I was able to figure out what was going on because the thing was turning on and then turning off again. So there was no race condition. It was easy to realize what was going on. So in this, let's say, a little bit more complex system right now, all of the discovery, all of the communication, rebalancing, all of that is done for you by Dapr. How do you do that? So how do you interact this? The only thing you have to do from your application is just invoke some methods through HTTP or gRPC endpoints. So pretty simple stuff. You define your methods on the actors. As if not thinking about concurrency at all, you define it as if you know that it's going to run in isolation, so your developers don't have to think about that part. You can prevent errors in the future, right? And you can just call these simple methods. So what do we get in 1.14? In 1.14, we get all of this, but you can now deploy it in multiple namespaces, which has been something that people have been asking for. This is important, not because it's just a good practice, but sometimes it's even a compliance requirement. So it's kind of important. Okay, let's get to the demo. It's a very simple one. This is Conductor representing just a little Kubernetes cluster in kind that I'm running online or locally. Sorry, that I'm running locally. And in here, you can see that I have one actor type deployed in two different namespaces, named NS1 and NS2. Right now, I don't have any activity in the actors, but if we switch to this little app that I did, on the left, we have a little mobile app simulator that's going to control our living room, garden, and bedroom lights in namespace 1 and namespace 2. And these are the actual lights represented by little yellow circles on the right. So row 1, the top row represents namespace 1, and here we have namespace 2. So if I go click, we see that only the light in NS1 lights up. The light in NS2 is not influenced. So if we do, simulate a little activity here, and we go back to our cluster in a while, after a while, we're going to see some activity coming in for our actors. Okay. You can find this demo. Let me show you the code a little bit. So what did we do here? We have a client and a service app. So the client would be what we simulate with the phone app. It's just a simple Flask application where we hard code a few actor IDs. Just a few checkboxes that control the state on screen, and then we create the actor proxy, and we call the setMyData method on the actor, which is remote, by the way. That actor is hosted on a different service, but all we need to do is just give it the ID and call the setMyData and pass it the status. So Dapr figures out where it can find that actor, which sidecar would be running it, and then when that reaches the service, so this would be the light controls service here. This is a fast API application. Here we are. When it reaches here, it finds the actor. This is our actor that has this setMyData, getMyData, and this is what happens. We just log a little message here, so you can see the setMyData when we are turning it on, turning it off, and it logs the namespace in which we are working. Here's namespace 1, namespace 2 logs over here. So we're using Pusher to just send the real-time notifications, so we can see that nice light toggle on screen. Okay, so if you want more details on this, you can check this repository, and I can answer your questions in the QA. Thank you very much. The key takeaways here would be that we can now have same actor type in multiple namespaces, and it's important to know that each namespace is going to require a separate state store. If you're looking to upgrade to 1.14, so you can make use of this feature, you don't have to do anything if you're using TLS. So as long as you're using TLS, and I hope you are, I guess you are in production, you don't have to configure anything extra, anything special. This is just going to work for you directly out of the box. If you're not using TLS, then there are some limitations, but you can read about them more in the release notes. Thank you very much.
Well, thanks, Helena. That's amazing. I love actors. I think they're an amazing, creatable, amazing technology. It allows us to kind of represent state and code together. I think the best thing to do now is we just sort of dive in and talk to about a real world use case about using this. So let's kind of move on now to Alice and kick it away on talking to Joao on what we're going to do, what use case we've done with multi-tenancy actors.
Thanks, Mark. Yeah, so we actually don't even have a slide to share. So we're just going to kind of go through a little bit about the use case. My name is Alice Gibbons. I'm a customer success engineer here at Diagrid. And I have here with me Joao. Would you like to introduce yourself?
Hi, thank you for having me, Alice, and everybody. Hi, everybody. My name is João Abrantes. I'm the platform lead specialist in Schreder Hyperion, which is a technological pole from the big company Schreder that we belong to, ancients in lighting and public lighting, and now delving into the world of smart lighting and IoT overall and smart cities.
Yeah, so you would think we would have planned that. Elena's demo was a lighting demo. We didn't even actually plan that. So that was good. I'm glad that we did that. And I don't think you gave your role at Schreder Hyperion platform. Yeah.
Yeah, I'm a platform lead specialist in my team and on the cloud team of my company.
Awesome. Yeah, well, thanks for joining. And I just want to start off with talking a little bit about how long you've been a Dapr user and really what your application is that's using Dapr today. Like, what problem does it solve for you?
Very similar to how Elena put it, we have IoT devices. And initially, let me start for saying I'm a Dapr user for 5 years, and gladly so far. Amazing work and amazing support from the community have been good drivers to keep us partners and in business with you guys, even at Diagrid. And essentially, what we are trying to tackle here is the IoT paradigm. We have thousands of devices. Different devices communicate in different manners with different payloads, with different frequencies and cadences, with different throughputs. And to solve this, we need to treat, at least in our scope, we treat each type of device as a family, and then within that family, we have certain rule sets that we must take into consideration. So if we need to interact or process telemetry to store state, as Elena said, we use the Dapr actors to save that state, but also if the user wants to interact, like Elena also perfectly demoed, again, that demo was quite on point to kind of describe our use case. We also use the Dapr actor to store the intent to then interact with the device and come back with the feedback.
Okay, so then, simplifying it also for those who are maybe a little bit newer to actors, each of one of your devices is an actor as well, right? And then you have kind of the device families, okay, which are specific to kind of the products that you guys offer. Am I oversimplifying?
No, that's pretty clear. That's how we do it.
Okay, awesome. And then, so you're obviously using the actors for the devices, as we talked about. Can you talk a little bit about the scale perspective, or really just give any numbers on kind of where you guys are going or where you have been?
Okay, yeah. First of all, this all started because we identified the actor paradigm to be the right one to choose. But then again, orchestrating it all, developing it from scratch, thinking about reliability, scalability, and all of that would be just like 90% of the development. And the odds to do it right the first time would be hard to accomplish in the time we had to deliver. But working with Dapr really helped us that way. Regarding values, we are growing as the business of IoT and smart cities is growing. We are surfing that trend, if you will. And we started with 100,000 of devices, and we're about to reach millions. And the goal is to really be at even more millions in the upcoming 2 years.
Wow, multiple millions. All right, that's awesome. That's awesome that the scale thing, and that you're going to hopefully get to that scale, and hopefully some of those improvements Cassie touched on earlier in the session can come back to help you guys a little bit, right?
Yep.
Awesome. And then, you know, one of the other things we're talking about that namespaced feature that is new in Dapr 1.14. I know this was an important feature for your team. Can you talk a little bit about why that feature was important and kind of just like what it's going to help you with going forward here?
Yeah, certainly. So as I said, we have different device families and they behave differently. They have particularities to the way they work. And one of the things we started to see is that at some scale, some families would affect some user experience that do not have any devices of that particular family that was affecting the load. And since we are using one single state store to host all of the state of the actors, many writes of a family would affect the concurrency to the state store of a device from a different family. So we started to thinking, okay, first, of course, we need to optimize how many times we go to the state store, of course, and that part is done. But thinking ahead, we need to start thinking about sharding. And although multi-tenancy is by default, the name kind of brings your mindset to thinking, okay, I have multiple tenants and they should not cross one another in terms of usability. Here we're thinking about first device families should not cross one another because our cloud is shared and it's the limits are drawn logically. But also later on, even within the same family, there are family of devices that will no longer be produced. Some of them are going to start production and the others are growing. So we need to also consider sharding later on for different, for the same device family, and multi-tenancy or namespaced actors will certainly help that way. That way we can put devices from a certain family in multiple state stores under different namespaces and grow. We can scale that way better than just relying on a single state store.
Yeah,
and
I can see that.
Keep on. There's only so much we can optimize when we're reaching the numbers we're reaching.
Yeah, no, that makes total sense. Like being able to have a different state store per namespace, as Elena mentioned, and then have that same actor type, so same device family across namespaces, especially for like the migration period, kind of feels like it is necessary, at least for what you're going through, at least right now.
Yeah, and you mentioned it, and I completely forgot it because the migration phase will be critical. There will be at least a certain amount of minutes to hours where we'll have to support old, migrate to the new, and then shut it down. And for that time, without namespace actors, it would be almost an obliged downtime that we'd have to conform to with our customers, and we don't want that. Yeah.
Okay, awesome. Yeah, well, thanks. That's a great explanation, and thanks for diving into that with us.
Right. Thank you for having me.
Yeah.
Thank you.
Thanks a lot, Alice and Joao. Another thing I want to mention before we continue is later this year, there will be a Dapr Day. So it will be like a virtual conference all about Dapr. So and the CFP, the call for papers, is still open for like only a couple of days because it's going to close on August the 5th. So please scan this QR code that will lead you to the Sessionize page where you can submit a session for Dapr Day. So I really invite you to submit a session.
And that's Dapr's 5th birthday, isn't it, Mark?
Yes, so this is really a special occasion, right? Because we did like a Dapr Day earlier in the year, but this is definitely a bigger one. I will also invite some special guests as well. So yeah, this will be like a big event.
Yes, it's going to be a big event. It'd be great to have CFPs submitted, and we'd love to hear you talk, especially from people from the community. So we've got a great talk, particularly around your scenarios and what you built with Dapr. Please put a CFP in. We'd love to hear from you.
Exactly. All right, let's move on. Oh, sorry.
No, you're good. Yeah, back to me for just a quick introduction here. Yeah, so I wanted to just give a brief overview onto Dapr metrics because the topic that we're going to talk about next is optimizing Dapr HTTP metrics for path matching. It's a very specific feature to Dapr 1.14. And also, if you don't have any idea about Dapr metrics, you won't have any idea about this feature. So essentially, I just wanted to give a quick brief overview to kind of get us all on the same page. So Dapr metrics, are enabled by default, and they are essentially the There's over 150 of them that come out of the box with the project. Essentially, each of the Dapr sidecars exposes a Prometheus compatible metrics endpoint that can be scraped. You can use like OpenTelemetry Collector to scrape that. You can scrape it manually. There's a ton of different ways to do that. The metrics themselves, like I said, they are enabled by default and they are exposed typically on port 9090. And as I mentioned, there's a huge number of these guys. So everything from, Dapr has both HTTP and gRPC protocols, client server requests there, latencies. There are metrics specific to the control plane. So, we talked about some of the control plane services already in this webinar. Things like, the number of sidecar injections, the services that were created by the operator, the actor hosts, like we were just mentioning in the previous session with Elena and Joao. And then many other things, right? So Dapr, since it kind of spans that component or the infrastructure application layer, there is also a ton of metrics in there around component counts and latencies. Now, these are all really great, except if you're using all of these metrics, sometimes this can be too many. And this is where kind of cardinality comes in. And these, I should have mentioned as well, you can configure these metrics via a configuration file. So on the bottom right of the slide there, you can see kind of a sample configuration file. There are a number of configuration options that you can add. And things like the cardinality and the latency buckets are both features kind of enabled in Dapr 1.14. And one of our engineers from Diagrid, Nelson, has implemented a feature for HTTP path matching to kind of improve the cardinality problems that we were having with previous versions. So with that, I just wanted to pass it over to, unfortunately, Nelson couldn't be here today, but he recorded a video for this. So I just want to play the video of his now.
Hello everyone, I'm Nelson, software engineer at Diagrid. Today, I'm excited to talk about optimizing your Dapr HTTP metrics with a new API called path matching. In this session, we'll cover what high cardinality is, the limitations of using regexes, and how path matching can improve your metrics management. We'll start with an overview of high cardinality, explaining why it's a challenge and how it can impact your system's performance and security. Next, we'll discuss the current approach of using regex for metrics filtering, highlighting its complexities and drawbacks. Then, we'll dive into the path matching API, demonstrating its benefits and how it simplifies metrics configuration. By the end of this session, you'll have a clear understanding of how path matching works and why it's a valuable tool for anyone looking to enhance their observability practices, and we'll also see a live demo to show path matching in action. Let's get started. Let's begin by defining high cardinality. Cardinality refers to the number of unique values in a collection. In the context of metrics, high cardinality means having many unique values for a given label. This can lead to increased resource consumption, higher operational costs, and performance issues. Moreover, high cardinality can expose vulnerabilities to attacks like distributed denial of service. It is a time bomb indeed. High cardinality makes your metrics harder to analyze because there are too many unique data points, which can be overwhelming to your monitoring systems and hide important trends. This can result in slower query performance and longer troubleshooting times, making it harder to keep your systems running smoothly. Additionally, high cardinality can strain your storage as more unique metrics require more space, thus increasing the costs. In short, high cardinality can make your monitoring tools less effective, turning a simple task of monitoring and analysis into a resource-heavy and complicated process. Fixing this issue is crucial for keeping your system efficient and secure. To address these issues, Dapr introduced the Path Matching API for HTTP metrics. This API allows you to specify the paths that are most important for your observability needs. Benefits include better memory management, enhanced security, and improved performance. Given that path matching happens in a Dapr out path, the implementation leverages the Go standard library router, ensuring efficient and scalable path matching. This means that the path matching API not only simplifies your metrics configuration, but also maintains high performance under heavy loads, making it a robust solution for high throughput environments. In the link below, you can find a detailed description of the proposal, including technical specifics and configuration examples to help you understand the full potential and application of this API. Previously, Dapr Rules API allowed defining regex patterns to reduce cardinality. However, regex patterns are hard to maintain and can be CPU intensive because each metric requires its own regex. Path matching simplifies this by letting you define important paths just once. Applying the rule to all metrics. For the best results, use path matching API with increased cardinality, flag set to false. On the left side, you can see 3 separate rule configurations for different metrics. Each one of these is transforming the same orders endpoint. This setup must be repeated for every metric. On the other side, path matching makes this process much simpler. With path matching, you define a single entry that applies to all metrics. This simplicity is a major advantage of the path matching API. For our demo, I've set up a simple scenario with 2 Daprized applications. A user service that's calling order service via service invocation on 3 distinct endpoints: orders, payments, and basket. To demonstrate the impact of high cardinality, we'll first observe the system without path matching enabled, highlighting the resource consumption and performance issues. Then, we'll switch to a cluster with path matching enabled, showing how it effectively reduces the memory, the number of unique metrics, and improves the overall efficiency. This comparison will clearly illustrate the benefits of path matching in a real-world context. Let's start by looking at our high cardinality cluster that does not have path matching defined. If we look at the configuration that this cluster has, on the metrics, we only have the increased cardinality defined and set to true. On the applications, we have 2 applications. We have an order service that sits around 150 megabytes and a user service sitting almost at 400 megabytes. If we look at the user service, we can look at throughputs and see the HTTP latency for the P95. This graph has methods and paths. If we look at the paths, we see that we have 1 entry for each call on the baskets endpoint, on the orders endpoint, and finally on the payments endpoint. And this is something that we don't really care about in the end of the day, because what we want to know is what's my P95 on HTTP latency in the basket, orders, or payments endpoint. We don't really care about individual latency for individual IDs. Let's now take a look at our path matching cluster. If we look at the configuration, we can see that we have path matching defined for orders and payments, but no baskets here. Because baskets, for me, it's not a relevant endpoint. We can think about a business and the endpoints that are relevant to our business. And if they are not relevant, and if we don't care about them, or if they don't provide any value, we don't need to waste resources or anything else with them. We can just ignore them with path matching and only choose the endpoints that are relevant to our applications. If we go and see the applications, we have the same 2 applications, but with definitely lower values in memory. The order service sits around 70 megabytes and the user service around 130 megabytes. It's almost a 4 times decrease in the memory consumption. This time, let's look at the order service. If we go to throughputs, on the P95 for the latency, we can see a different thing that we have seen before. We can see that it loaded a lot faster and the information is very well organized, unlikely the other scenario where we have different entries for each ID. In this case, we have all our calls to orders, payments on both get and post endpoints aggregated by the order ID and payment ID in this case. This is really powerful. In conclusion, path matching is a powerful tool for reducing high cardinality near Dapr HTTP metrics. It's easy to use and offers benefits like better memory management, improved security, and enhanced performance. By simplifying the configuration process, path matching not only allows you to make your metrics management more efficient, but also reduce the likelihood of errors and maintenance overhead. This streamlined approach can significantly improve your system's reliability and scalability. Thank you for listening, and I hope you start leveraging path matching in your projects. Feel free to ask any questions.
On the metric side of things, Alice, what are some of the common metrics that people like to look at most of the time when people use them?
Yeah, I mean, I think that is something that we have done pretty well on the Conductor side of things. Honestly, I think the client server metrics for both HTTP and gRPC are definitely commonly used for things like service invocation, but then also for reaching out to the different kind of components behind the scenes. And then I would say the component metrics are also kind of unique to Dapr, right? Because they give you some view into your infrastructure that you might already not have. Just with your regular metrics, or sometimes if you have a service mesh or something else, you would get kind of metrics from your applications, but having those infrastructure metrics as an additional layer is kind of really nice there. Yeah, a good question.
Right, so with us here is Mauricio Salatino, who's going to talk about Dapr Shared. Welcome, Mauricio.
Thank you very much for having me. Yes, let's talk a little bit about Dapr Shared, a project that I've started, I don't even know when. It was almost 7 or 8 months ago. And since then, tons of things happened there. So let's talk a little bit about it. So as Mark mentioned, my name is Mauricio Salatino. I'm also working as a software engineer for Diagrid, working on the open source stuff and also doing some things in the CNCF on different working groups. But today I'm here to talk a little bit about Dapr Shared, a project that you can find now into the Dapr Shared repository on the main organization. And basically what Dapr Shared does, it's enable new deployment strategies for Dapr. We are used to work with Dapr as a sidecar, but there are some scenarios where that will not work. And that's why I started thinking about something like Dapr Shared, and that's why we created this. So when and why do you need Dapr Share? That's the main question that I will try to answer. Hopefully, by just showing you a couple of scenarios, we can figure out the main use cases and the main reasons why, again, this project was created. So for some use cases, sidecars might not be an option. And I find myself talking with teams that maybe they cannot deal with sidecars. Their operation teams, they have been burned in the past with service meshes or tools that were using sidecars. And then when they see a tool that is using sidecars, they have a strong pushback. There are other situations when you want to decouple the lifecycle of your application from the Dapr runtime and the Dapr APIs. And most of those cases that I found in different communities are related with serverless computing, where you have workloads that can be upscaled or downscaled dynamically. And the relationship between Dapr and the applications might not be suited for the sidecar model. So, and that's pretty much aligned with my personal story. I joined the Dapr project about 1.5 years ago, almost 2 years now. And before that, I was working a lot with Knative. So for me, being a very practical person, the first thing that I decided to do is let's build some examples using Knative and Dapr. Knative is very associated with, with serverless and upscaling and downscaling your workloads based on demand, basically. So, the first thing that I said, let's try the state store APIs. Let's use Dapr for that and use the state store APIs using the Java SDKs or the Go SDKs. And I created a Knative service. And Knative works like that. It will look at the traffic going into your application, in this case, the HTTP traffic going to your application. And based on that, it will decide if you need to upscale your containers, create new replicas dynamically, or downscale it. So if you have more demand, it doesn't mean that one user, one container, multiple users can be hitting the same container. But at some point, when you have enough demand, Knative will start dynamically creating new replicas. And because it will scale the pod, every time that you have a sidecar inside the pod, you will get more sidecars with more replicas. And this works perfectly well because then you can keep calling the state store APIs as you would do with any application that runs on Kubernetes. The problem, and in general, it's not the problem, but in this case, if there is no demand, Kubernetes will automatically downscale to 0 your containers, and with that, the Dapr sidecars will go away. So there will be nothing here connecting to the storage at that point. But whenever you have a new request, Knative will spin up a new replica, and in this case, it will start the application container, but also the Dapr sidecar. those two needs to connect, and then you can send the request to the storage, right? In this case, it works pretty well. As soon as you wait for the Dapr container to start and everything is up and running, you will be able to send, HTTP or gRPC request to the Dapr APIs. The next thing that I said, it's like, let's work with PubSub now, because, if you are building functions or serverless applications, they will want to store state, but also they will want to exchange messages. And for publishing messages, it pretty works the same as with state store. You're going to send a request to the, to the publish API on the sidecar, and then that's going to put a message into a topic, into a message broker. For publishing messages, everything works well, because if the application gets downscaled, nothing happens. But when the application starts again, you need to wait for the sidecar and the application to be ready to then publish the message. And that works perfectly. The problem appears when you are doing subscriptions. If you are doing subscriptions and you're working with this serverless model, the problem is that the subscriber itself, in this case, the Dapr sidecar, will need to be running in order to actually subscribe to messages into a topic on a message broker. If you get this situation where your application gets downscaled, there is no Dapr sidecar subscribe to the message broker. So those messages will never be picked up from the queues, from the topics, and your application will never find out that there is a message, waiting to be consumed there. And I said, okay, that might be a limitation. So let's jump into, service-to-service invocation. And service-to-service invocation also works like that. You're going to be sending a request to the Dapr sidecar, and that sidecar will contact the application B sidecar in order to forward the request to the application. That's kind of like the interaction lifecycle. If the application B gets downscaled, there is no sidecar to connect, right, to send the request to. So there is like that request will get lost or probably will fail to be sent because there is nothing waiting for that request. So we need to solve it in a way. And that's the main reason why I started thinking about deploying Dapr, the sidecar itself, not as a sidecar, but as a separate entity that our applications can connect with. In order to do that, I needed an example. So I went to the Hello Kubernetes Quick Start in our documentation that basically provides two different applications, a Python application that is sending requests using the service-to-service invocation, APIs to the Node application that is basically receiving this request, gets the payload from the request and store it into the state store. That's a very simple application. But if we want to decouple the lifecycle of the application from the Dapr sidecars, again, we will need to separate these life cycles. We will need to run Dapr as a separate entity right besides our applications. In this case, what I'm showing here is using Dapr Shared in order to separate, not to run Dapr as a sidecar with the Node and the Python app, but just to share Dapr as a separate entity. You can notice here that I have two different entities because, again, I want to maintain application identity and app IDs in this case. So I need to have two Dapr containers running in this case. The advantage of doing this is that now you can restart your Node and Python application. You can downscale the applications, and if you have subscriptions or service-to-service invocations, Dapr will still be running. So it can deal with that and then notify the application back if it's like an incoming message to the application. And that can trigger something like Knative to boot up a new replica for your application if it was downscaled. So in order to achieve this kind of like diagram, this separation of concerns, separation of lifecycle, what Dapr Shared provides is two different modes that allows you to deploy Dapr using two different Kubernetes resources. The first one, and the most common one that I will assume everybody using Kubernetes will know, is the deployment approach, which basically will create a new Kubernetes deployment resource to deploy Dapr itself, like the sidecar itself. It's not a sidecar anymore, it's now a Kubernetes deployment. And Dapr Shared will add a service, so our applications know where to contact that instance of this, Dapr D container running. We also need to configure the way for Dapr D to connect back to the application, because if we get a subscription coming in or a service-to-service invocation, we need Dapr to contact the application back, and that's why we need to configure the app channel and the app port. Everything else should work the same. The second mode that is provided by Dapr Share is the daemon set approach, which is a different Kubernetes resource, which basically will help us to co-locate, or to make sure that there is one instance of this Dapr container in every cluster, in every node inside your Kubernetes cluster. Remember that Kubernetes cluster can have multiple nodes, and we don't want an application calling, Dapr in a different node because we will be creating a new network jump in there. If we can have that co-located in the same node that the application is, might be better, right? Like we will just reduce the latency between these two things. So I wanted to quickly show kind of like an example that I have here. I have some pods running in my cluster, and these pods are the pods created by the Hello Kubernetes, quick start tutorial. The only thing that I did is I commented out, the annotations, because again, I don't want to use sidecar injection. So I commented the Dapr annotations for my workload, so the sidecar will not get injected. I have the Python application and I have the Node application, both commenting this out. And that's why if I look at the pods here, there is no sidecar running in there. I have also Redis instance that I will use as the state store, and I have like the, the Redis component here, which is the state store connecting to that Redis instance. But I have no sidecar, right? Now, if I want to look into this application quickly, I wanted to see that it's failing because there is no sidecar, but the application is using the Dapr APIs, right? So, for example, the Python application here, every second is failing. It's trying to send a request to the Node application, but it's failing because it doesn't have a sidecar, basically, right? So that's one thing. The other thing that I wanted to show is that I have a Kubernetes cluster here with 3 nodes. So 3 worker nodes, the worker 2, and the worker 3. And the pods here of my applications are running on different nodes, right? Like the Node app is running on worker 3, and the Python app is running on worker 2, right? So how do we add Dapr shared instances into this application so the application can work with Dapr, but not as a sidecar? So in order to do that, we will run a couple of commands here. So you will see that in order to create new Dapr shared instances, we use Helm. We use a Helm chart, which is basically located in this repository. And then we configure some parameters, in this case, the application ID, the app ID for Dapr. And then the strategy that we want to use, we will start with deployment. So we are creating a new instance of Dapr, the Dapr Day container here, as a deployment inside of our cluster. And I will do the same for the Node application. The Node application, because it's receiving these service-to-service invocations, we need to set up a couple of more parameters. In this case, the remote URL, which is the URL of where the application is running, and the port that the application is using. So Dapr can connect back to the application whenever it's needed. So now that I created 2 instances of Dapr Shared, I can list my pods again. I can see that everything is running here. And I can go here to the Python apps again, just to list the logs. And you can see that the application is not failing anymore, right? Like before it was failing every second. Now it's actually sending the requests correctly to the Node app. And we can check that the Node app is receiving the request and then storing the payloads into the state store. Yeah, we're getting 1 request per second and we're storing that into the state store. So that's pretty much seeing the application working. But as I mentioned before, we have 2 different flavors for Dapr Shared. And the main reason for that is that if I show here now where the Node application is running, it's running on the worker 2. Look at that, like we got lucky and now Dapr Shared got deployed in the same worker. But if you look into the Python app, it's running on worker 2 and the Dapr Shared instance is in a different node, right? For some scenarios, that's fine because we like latency there, it's not that bad. But for some other scenarios, we want to make sure that at least we have an instance of Dapr Shared in every node of our cluster. And for that, we use the daemon set approach. So I will delete the Helm charts, the Dapr Shared instances that I've created before, and I will recreate this with the other strategy, which is the daemon set strategy. The daemon set strategy will create 1 instance of the Dapr Shared, like the Dapr Day container in every node inside the cluster, which requires more resources, but at least we will reduce like network latency. So let me do that again here for both of the applications. I can list the pods now, and you will see now that I have 4 different instances, because remember that we have another node for the control plane. We shouldn't be creating that in there, but you can add annotations and taints, so that doesn't happen. This is failing for some reason. It fails because Redis is down, and for some reason my Redis installation tends to go down after some minutes. I think that I'm using some in-memory parameters there, but let me see if I can delete this quickly and then see if it restart correctly. All the replicas here of Dapr Shared will restart, connect to that state store, and then the applications will keep working. No matter which strategy you use, like the applications should work, but depending on your use cases, sometimes you will want to reduce latency by just having making sure that there is an instance of that Dapr D container in the same node where the application is. So trust me on that, that will work. I will want to close this presentation with kind of like, again, a couple of things that I want you to take away. From Dapr Shared, like basically helps you to decouple the Dapr runtime from your application runtime. It comes with those two flavors, like deployments and daemon sets. It requires the Dapr control plane to be installed, right? Like I'm not, removing the Dapr control plane. You need the control plane there. The only thing that we are doing is switching from sidecar to running as a deployment or as a daemon set. For that same reason, we will have one Dapr Shared every time that we have a Dapr D container running. We will need to have a Dapr Shared running if we want to, use Dapr Shared for our applications. It doesn't use the sidecar injector, as I mentioned, so we don't need the annotations. And you can create new instances of Dapr Shared by creating new Helm releases of these charts that I've been showing, right? Like just running this command that you can see down in the screen and setting the right parameters, you will create a new instance of Dapr Shared. Dapr Shared doesn't handle more than a single app ID per instance. So we are not doing that. And we're not doing that because we want to keep service identity, right? Like we want to keep like a Dapr D running instance associated with an app ID. Dapr Shared doesn't automatically create Helm releases for now, and it doesn't have a new Kubernetes controller. That's an idea that it's floating around, but we haven't implemented that. And that's up to the community to decide if we want to go that way or not. And one more thing that I wanted to mention is that if you go around looking into different serverless frameworks that are using Dapr and things like Knative or Keda, you will see that they will create their own Dapr Shared version, because actually you need to have these different deployment models if you are kind of like into the serverless space. So that's the example of Open Function. They have something called Backend as a Service using Dapr, and for that they created something pretty similar to Dapr Shared. That's why also I felt that we needed to provide like an official version of these mechanisms for different implementations to just consume instead of reinventing the same thing. I think that that's pretty much what I have wanted to show today. So if you have any questions, please feel free to reach out.
Well, that's super cool, Mauricio. Actually, there is a question that does get asked. So I'm going to pose this to you because Gilles asked,
Sure.
how do you manage the scaling of your Dapr D replicas when you scale the consumers of your Dapr Shared instances via Knative? So
that's a very good question. So how do you manage the scaling of your Dapr D replicas when you scale the consumers of your via Knative? Yeah, so you can scale it. So if you're using, for example, deployments, you will scale it in the same way that you scale any other deployment. You can change the amount of replicas of that deployment in your Kubernetes, manifest or your Kubernetes resource. Right now, we are not doing any magic in that space. That's why I think that at some point, having some controllers, not to only create instances, but also to manage actively those instances will make a lot of sense. But still, like something that we can create a proposal for if we think that there are enough use cases to do that dynamically.
Yeah. And certainly having these different deployment models are really good in terms of different kind of use cases, yes, as you went through, having it deployed on a per cluster basis, per node basis, and and then, the sidecar basis. So, those different scenarios are really, seeing them kind of in everything from resource constrained scenarios to, to running them in production. Is that correct?
Yeah, that's correct. Yep.
Yeah.
Pretty good.
Great. And so just to be clear, Dapr Shared isn't actually part of the 1.14 runtime. It's in its own repo. So it's been moved into the Dapr org underneath that. Mauricio gave you a bunch of links inside there. This is one of those things that we're taking through to a production scenario. So the more feedback we get on this, the more we can get this into a stable version of it and have this sort of completed and done. So thanks, Mauricio. That's fantastic.
Thank you, folks.
We move on to my favorite feature now in 1.14.
Yes. Let's need move on to the streaming subscriptions.
Hi everyone, my name's Josh. I'm an engineer here at Diagrid and I'm also a maintainer of the Dapr project. And today I'm going to be talking about a new feature that we've added into 1.14, which is streaming subscriptions. So before kind of diving in on what streaming subscriptions are and things like this, I want to talk a bit about the kind of motivation behind creating this API, because of course we already have two existing APIs for subscribing to PubSub messages, PubSub topics in Dapr already, but we felt that there, as the Dapr project, lacked some potentially some UX benefits, as well as some kind of technical limitations with using those methods. So Concretely, the motivation for adding them in 1.14. So subscription topics must be known before runtime. So what do I mean by this? In Dapr today, when you subscribe to a topic, you need to know the topic name and the pub sub name, and put those in the manifest file or what have you. We'll talk about a bit about that in a sec. It's also the case that you're not able to dynamically stop or start those subscriptions as part of your application code. It's also the case that today that to subscribe to topics, you must have a HTTP or gRPC server running as part of your application, and it also follows on that you need an application defined at all in Dapr D in order to use the existing subscription APIs. So as I mentioned, we already have two methods for subscribing to topics today. The first one being declarative. So this is where you define your subscription manifest as as a file if you're in self-hosted mode, for example, or as that YAML manifest that you install into Kubernetes to then be consumed by applications if you're running there. It's also worth noting that we've added hot reloading to dynamic subscriptions in 1.14. This is behind a feature gate. And there'll be documentation on how you can enable that. But what that means very quickly for hot reloading is that if you edit this YAML file, in self-hosted mode or in Kubernetes, you do a kubectl edit or something like this, or you delete the manifest, or you add the manifest or add a new manifest, this will be reflected in your application, and they'll consume the new subscription edit or changes or additions. So that's declarative. We also have programmatic. This is where you define your subscription values in code. But importantly, it's the case that number one, these subscriptions are only read during the application start time. They can't, they can't be changed over time. They can't be stopped or started. And the same, you have to have a server running in order to subscribe subscriptions in this way. So the new subscription method that we add is what we're calling streaming subscriptions. It ticks all those boxes that we've just been talking about, basically. So you're able to dynamically add and remove topic and pub sub subscriptions whenever you'd like in your code. The variables that you give the API, you can infer at runtime. These could be variable. You don't need a server, which means no ports open and things like this. And on that particular kind of server or port issue that I keep coming back to, this is quite interesting for particular deployment models where you don't necessarily want to be opening a port on your application to consume pub sub topics. So, for example, a good example of this would be Catalyst, for example. I want to subscribe to a pub subtopic in Catalyst, but I don't necessarily want to be putting an app callback URL. So I don't necessarily want my application to be, exposed over the public internet or something like this, or want to use kind of a tunnel in order to consume those messages. So I've got a code snippet on the right here of this new API, and it's pretty simple. So if you look at line 17, we've got clients subscribe with a handler. So I'm using a particular function based subscription. In this case, we've got another kind of Go SDK kind of method that I'll show you in a second for this API. Yes, we're subscribing to my pub sub on orders. And then on line 31, that's the function that's going to get called. So you can see in that function, you'd put, whatever you're going to do to process that message. And then also worth pointing out is that line 28 there, that stop function. So that stop function is going to be the thing that that unsubscribes from that particular pub sub topic. And then, of course, if we try to subscribe to a pub sub or something like this, for example, that didn't exist, there would be like the line 25 there, that kind of error handler that will kind of error sooner. To kind of give you an error code on what the pub sub didn't exist or whatever error it might be. Cool. So I'm now going to go ahead and show you a demo of this in action. I think it will give you a lot more context on what this API means and why it'd be interesting for you to use. I certainly believe that streaming subscriptions will be the default or likely the kind of API that most people would be using, and most of the time I think it would be strictly better than the rest because of kind of the ease of use and that kind of dynamic nature of it. I think is much more familiar. And then once I've shown the demo, I'm going to go ahead and kind of talk a bit more about the kind of technical details on how this feature is working behind the scenes. But yeah, let's crack on with the demo. So I'm going to open up Conductor here. So you can see that I've got 2 applications installed. So I've got a Kubernetes cluster running. I've got two apps running. So one's called Pub, one's called Sub. I'm sure you can probably guess what both of them are responsible for doing. And yeah, you can see that I've got one publish application running at the moment, and then one subscription application running at the moment, and no publisher running at the moment. Just because I kind of want to show you that publishing happening in kind of real time. It'll give a lot more context that way, I think. And also wanted to show that we've got one subscription already active from that subscriber application. And that type there is of type streaming. And we are subscribing to the start message topic on the pub sub messages. So next I want to show you the code of these applications themselves. And I think first I'll show you the publisher. I think that would be best. What we're doing here is the publisher will start up. What's going to happen is the publisher is going to send a message on this start message topic. You might be able to see where this is going. So we're sending a random string on this start message topic. Then in this for loop here that will go on forever until the application shuts down, is we're going to be continually sending messages on that dynamically randomly generated string, and we're going to keep sending messages on that topic. And then once the publisher shuts down, we're going to send this close string here on that topic. So you can see where this is going. The idea here is that this publisher is going to send to the subscriber, this is a new topic that I want you to subscribe to, and then keep sending it messages on that particular topic. And then once we're finished sending messages on that topic, we're telling the subscriber to unsubscribe from that topic. So if we head over to the subscriber code, we can kind of see this in action. So the first thing the subscriber is going to do is going to subscribe to that start message topic that we just saw a second ago. And then it's going to, in this for loop, receive messages from that start message topic, and we're going to handle that subscription message. And what that is doing is dynamically creating new subscriptions for that dynamically created topic. And then we're going to pull messages from that new topic, and then we're going to wait for that close message to unsubscribe. So once we hit a close message, we're going to return from this function, and that is going to close the subscription. You can see here. Yeah, and this will go on forever. And then once this shuts down, this also as well closes the subscription here. Cool. So let's see that running in action. I think it will give, be much clearer to see what's going on that way. So I'm just going to follow the logs here on the subscriber. We're going to see it log out some messages in a sec. And as I mentioned before, we've got no publishers running yet. So I'm just going to scale up the number of publishers. Let's start with 1 just for now. So I'm going to scale up publisher, and you can see here that we received our start message from this kind of random string here, and the subscriber has subscribed to that random message topic, and just like we were talking about, it's now going in a for loop and sending new messages on that particular topic. And of course, I can scale up the publisher to 2, and we should see here, here we're now subscribing to those 2 topics, and obviously I can maybe scale up to 3 as well. You can see here that kind of turning through those 3 kind of dynamically created topics. And of course, if I scale down, based on that kind of close message protocol, I guess, that we defined in our code, that's going to unsubscribe from that particular topic. And so, in this case, you can see that the number 3 topic has now been unsubscribed to. We're only seeing 2. Yes, you can see here that we're stopping subscription for that particular topic. And of course, if I scale back up to 3, we're now subscribing again. And this has an index of 4, of course, because this is the 4th publisher that was run. Cool. And if we go back to the Conductor platform as well, you can also see the subscriptions happening in real time in the platform as well. So you can see here that they're from messages. We've got compassionate care here, and what have you. And yeah, you can see here that they're all of subscription type. Great. So let's go back to the slides here and go to the next slide. Yeah, so now I wanted to talk a bit about the technical implementation of how this is working behind the scenes. So PubSub subscriptions today, as I've been mentioning, the subscriber app opens up a HTTP or gRPC server. And then Dapr D is going to be then configured to subscribe to particular topics through either that declarative way, through the manifest files, or the subscriber app will be telling Dapr D on that on its server what topics it wants to subscribe to, and then Dapr is going to be pushing the topic events to the app on a particular endpoint. So in this case, HTTP. I've got a kind of post there on HTTP at that kind of checkout endpoint. For stream subscriptions, it's different. We're going from a push-based model to a pull-based model. So you'll notice with streaming subscriptions that there's no concept of routing or path or anything like this. And that's because we're going over these kind of individual streams. So what happens is the application will make the initial connection to Dapr D. And this is importantly why we don't need kind of an open port on the app side, is because the application is making the streaming connections to Dapr D, and as part of that streaming connection, it will send something called an initial request, and that will contain all the information that's needed in order to subscribe to a particular topic. And then once that's been established and Dapr D makes the relevant subscription in the backend PubSub broker, it's then going to send the subscription messages over to the subscriber app through this kind of bidirectional stream. The current implementation is only in gRPC, but we do intend to implement this for HTTP as well. Great. Go to our final slides. Yeah, so just a recap. Streaming subscriptions, it's a new API for 1.14. It allows you to do fully dynamic topic subscription at runtime, like we kind of saw earlier. The topic names can be inferred through runtime, both the topic names and also the PubSub names. They could also be inferred at runtime. And yeah, there's no port, there's no server needed on the application side. So this is useful to deployments for like Catalyst, for example. And there's no subscription configuration. There's no YAML files or anything like this. Everything is part of your application code. Great. I've also got some links here at the bottom as well. I've linked to the original proposal, which outlines the implementation of this API for Dapr runtime. I've added the documentation, which goes into a bit, adds some more detail on how to use the API, as well as the Go SDK example on how to use it. Again, this API is currently only implemented in Go, but we'll be rolling out the API into other SDKs over time. Great, yeah. So that's all me on streaming subscriptions, and I'll hand it back. Thank you.
Yeah, this is really a great new feature in Dapr PubSub, and it's great to see yet another way of using PubSub instead of like a declarative and programmatic way. Yeah, I'm really excited about it. I haven't touched it myself yet. I'm definitely gonna try it out myself very soon. But yeah, this makes stuff like so much more flexible. So
yeah, I do want to draw out a couple of things here. I mean, for me, the simplicity of this is amazing because before now you don't have to host an HTTP endpoint on your application anyway. You can literally just have a function callback onto wherever you're running your code. And actually, we shared in the chat window as well a link to a documentation, a blog post that we posted on our Dapr on the Diagrid blog site, which kind of gives a great outline of the different types of subscription models and dives a little bit deeper into streaming subscriptions and how to use them all. But yeah, greatly simplifies how you do subscriptions and how they get called back to you. And it's going to be a game changer, I think, for how people build their applications.
Exactly, yeah.
Yeah, actually, and before you leave, I think that your own also point out is, there's another great benefit of this model. It's a pull-based model. So actually, that greatly improves handling the back pressure on your applications and how they get pulled and not only make it simpler, but actually reduces the pressure on your applications as well. So it's a great introduction all around, and I can see many of our applications changing from our current subscription-based model, from the declarative or programmatic to this streaming-based model.
Yeah, exactly.
Okay.
All right. I think it's time for our final session.
So with that, we're going to move on to Outbox projections with Jeroen. So take it away, Jeroen.
Yeah, thank you so much. Hi, everyone. My name's Yaron, co-creator of the Dapr project and core maintainer. And today we're going to be talking about a new feature in 1.14 called Outbox projections. Cool. So before we talk about projections, let's talk about the transactional outbox pattern, a very elusive pattern that is as easy to understand as it is difficult to implement on your own. And so what it does is it gives you the ability to execute a single transaction across a database and a message broker. And it might sound simple, but in actuality, it's extremely, extremely complex. And that is because you basically need to solve a very hard problem, which is the dual write problem. How do you write to two different places? It doesn't matter what they are, they're storage-based in a persistent way and guarantee that they're both written in, the same record while giving the transactional guarantee back to the client. Now, the Outbox requirements actually makes this a whole lot harder because we need to adhere to the following requirements. For example, if the state is saved in the database, a pub/sub message must be published as part of that transaction. But if the message must not be published if the initial state was rejected from the database, and then a state cannot be saved if there is no publishing message to notify any downstream subscriber. And if you think about it for a second, this is very, very hard to get right because there can be any number of combinations between message brokers and pub subs. And of course, databases are not natural message brokers. And if you're using a message broker as your database, then you're really weird. But you basically need to coordinate, state between two separate systems that are doing two totally different things. And this is just a diagram I grabbed that shows what this is, the command handler. To the left here is your application. It serves as transaction with your database. The database processes it and then commits it. And then, the application handler needs to send the event. This is what it would have looked like, based on the two-phase commit where the app first saved the message to the database and then sends the message all across to the event bus. But anything can fail, right? The database can fail, the event bus can fail. And so how do you actually ensure that this event is sent once the database message is saved, and that the database message is saved if a publishing message is going out? And so this is the main challenge that Dapr comes to solve for you by letting you implement this really difficult pattern with any number of combinations of supported message brokers and database Dapr supports. This is Dapr Outbox, and it essentially allows you to use any transactionally supported Dapr state store together with literally any pub/sub broker that is supported by Dapr. No limitations there, and it'll allow you to save database state and publish a message to downstream subscribers at the same time from your calling application. And there is a limitation here. So up until Dapr 1.14, the message that's going out to the pub/sub broker needs to be the exact same one that's being saved to the database. So you can see the JSON here that has the snake case. I like snake case, deal with it. This is awesome, true. And if you wanted to shape the message that's going into your downstream subscriber, that wouldn't work for you. So you would basically need to insert some boilerplate code where you would get the message in your subscriber and then maybe change it and then publish it to another topic, and then the other downstream subscriber will do what needs to be done with it. But that's too much boilerplate. So new in Dapr 1.14, we have Outbox projections, which allow you to fully control how the payload message going to the pub/sub broker looks like. And let's take a look at that now. So I'm going to switch over to VS Code here. Hopefully you can see that. And this is my downstream subscriber app. This is an application that needs to get a notification every time an order is saved into the database. This is the subscriber app. This is nothing too fancy, just a regular JavaScript application that subscribes to a pub/sub named order pub/sub and to a topic named orders. And it receives the events on this handler here. Nothing Outbox related, even nothing really, Dapr related, except for this piece of code that subscribes, which you can also do declaratively or through our new APIs that we've seen earlier. So this is all pretty simple, and we have a state store here. This is a Redis state store. So in this example, I'm actually going to be committing a single transaction between a Redis database and Kafka, which is really awesome. So I have state Redis. Let me just zoom in a little. And if you know Dapr, then, you know, looking at most of our examples, the highlighted part is what you'd see. You have the Redis host, Redis password. But here we're actually Outbox enabling the state store, and we're telling it, hey, every time you save a transaction into this database using Dapr's transaction API, we want you to publish the state into the order pub sub and to this specific topic. So we are going to go ahead now and look at our pub sub. This is our Kafka instance. This remains the same, unchanged. You don't need any form of special metadata like the state store. You can use it with any pub sub that you have. Literally any alpha, beta, or stable-based component that Dapr supports can be used with it. The supported state stores are the ones that support the transactional API capability. All right, cool. So now what I'm going to do is I'm going to use the Dapr CLI locally to run a Dapr sidecar, and then I'm going to save a state transaction to the Dapr sidecar, and we can see the projection in action. So I'm going to run this command here. This runs Dapr sidecar, Dapr run locally in my machine. Dapr is identity-based, so I'm just giving my app an identity. I'm setting the Dapr port so that I can call it, and I'm just telling Dapr what port my application is listening on here. App port 3000, this is what my Node.js app is listening on, and this is just a helper method that will launch the Node.js app locally on my machine after the sidecar is running. So let's do that, and we're already up and running. Dapr initialized in 128 milliseconds, connecting to both Redis and Kafka. It's pretty impressive. Very low latency startup time we have here, and we are up and running. Now I can go into Postman, and I can start executing a transaction. So first of all, let me get rid of this section here. This is what the Outbox would look like up until 1.14. So we have a transactional operation. We are committing it against the state store, which is Redis. And we have a key called order1. We have a value here. So there is a book, a fictional, well, this is not fictional books, just a fictional order. We are sending some JSON with the order ID, the type book, name, Samson's Apprentice, really good series of fantasy books by Robin Hobb, who lives 20 minutes next to me in Washington State. I really, really recommend reading this if you're into high fantasy types of books. So we are going to be committing this transaction, and we're going to be sending it. Great, 11 milliseconds response time. And so if I go into the database here, so using Dapr, I can just get the state, and this is the JSON that we saved. This is Dapr giving me the result that was saved into Redis. And if we go into our application here, we can actually see that this state transaction caused a pub/sub message to be sent to our application. Now, the calling application, which is in this case Postman, when it got the response back from the transactional API, would have also gotten the guarantee that once this state item was saved in the database, that this message would have been published to any downstream subscriber. Now, as you can see, this is the exact same message that we saved in the database. So we are going to go back here, and we are going to insert to our array this JSON here, and this is new with Dapr 1.14. So as you can see, this looks exactly the same as the one above, except for two changes. The first is we're basically telling Dapr, hey, look, this state item is an Outbox projection, which means that this operation will not be saved into the database. We're just telling Dapr, look, this is a projection of the order1 transaction order that we have here, and we just want to be able to shape the message that we send out. So if you look at the value here, it contains 3 fields. This is what gets saved in the database. This in line 20 here is just the field order ID. So we want to save the entire order in the database, but we only want our downstream subscriber to receive the order ID, which makes sense because we don't need all the information. And everyone knows pub/sub is really, really fast if you send only the data that you need on the wire. So this is what we're going to do. We're enabling the Outbox projection here. And so this is not going to be saved in the database, and we'll see it in just a sec. So now that we have this going, we can just execute this again. And if we go into the database and we get the state, we can see that we have the 3 fields that we saved. So this is not the projection state. This is the state that we wanted to save in the database. And if we go back into our application here, we can see that this message now only contains the order ID. So now I can completely separate the data that gets saved in the database from the data that gets sent into the underlying subscribers. And with that, we're also taking the Outbox feature from being a preview feature in 1.13 and 1.12 to being fully stable in 1.14. So you can go ahead and use this in production. Happy to take any questions.
There is one question from Arnold in the chat. He mentions, currently I'm struggling with the Outbox pattern since data is stored in SQL Server with Entity Framework Core and events are published through Dapr pub sub. It's not possible to contain it in a single transaction. I think I cannot use the Dapr implementation of the Outbox pattern. Am I correct?
So if you can use it with SQL Server, but if you're using Entity Framework Core, that's being done outside of Dapr.
Yeah.
So yeah, you cannot span the transaction across two completely different technologies. But if you commit the transaction with Dapr, then yes, you will be able to do that with SQL Server and whatever Dapr pub sub that you're creating.
Yeah, indeed. Yeah. So if you can drop the Entity Framework Core and use the Dapr State API, then you'll be golden.
Yeah.
Yeah, and thank you, Alice, for putting the link. Right. All right. Thank you very much, Jeroen.
Of course.
I will share my screen, and before we do the Lego giveaway, yes, of course, you might want to know how to actually get the latest Dapr release. And the 1.14 final release is not yet there. It's either going to be later this week or early next week. What will be there today is the 1.14 release candidate 8, if I'm correct. So you can definitely try that and also give us feedback. And there's a dedicated RC feedback channel on our Dapr Discord. So please feel free to try that. If you want to install it, you can either do it two ways. If you're running it locally using the Dapr CLI, I think a lot of people are doing that if they're familiar with Dapr. First, you need to uninstall the Dapr runtime using Dapr uninstall. And if you also want to uninstall the other containers that comes pre-installed, you can do Dapr uninstall --all. Then again, do a Dapr init to get the new version. If you want to check the version, you can do Dapr -v. More information on this link. If you're running it on Kubernetes, then the best way to do it is to use Conductor or Conductor free. Here you see the cluster overview. You click on your cluster, you check the Dapr version in the cluster insights. There's a label in there that highlights if there's an upgrade available, and you can actually select the upgrade version that you want, and you can click confirm, and that will automatically upgrade all of the sidecars to use the right version. All right, so definitely you need to have a look at the Conductor. The link is here in this QR and also written down there, diagrid.io/conductor.
Just one comment with the CLI version, you'll have to provide the version of the release candidate you want as you do the Dapr init. So that command there will just have to have the release candidate version added to it. We'll post it in the chat window.
Yeah, exactly. Yeah. Because the regular init will only do like the major versions and not the release candidates. Yeah.
And as you've seen through today, we used Conductor free through a lot of our demos today. It was in HTTP metrics. You saw it with streaming subscriptions. You saw it when we used it with actors. So, Conductor free gives you great insights into running Dapr on top of Kubernetes. And we've worked hard to get all of these features you see in the 1.14 release built into it all. So go and get hold of a copy of Conductor free, and then you can start taking advantage of all of these 1.14 features you see as part of it.